Hello students. In my previous video, we have discussed about the adjoint of a matrix. So what do you mean by adjoint of a matrix? Adjoint of a matrix is nothing but transpose of a cofactor matrix, isn't it? So what do you mean by transpose? Transpose means interchanging a row and column. So interchanging row and column gives the transpose of a matrix. So adjoint of a matrix is nothing but transpose of a cofactor matrix. So cofactor matrix means finding the cofactor of each and every element of a matrix. So that is a cofactor matrix. So how do you find the cofactor matrix now? Cofactor of an element Aij is nothing but capital Aij. So this is minus 1 to the power I plus j into capital Mij, where Mij is nothing but minor of an element Aij. Then how do you define the minor of an element? So minor of an element of this element Aij is nothing but is a determinant obtained by deleting the ith row and j column in which that element Aij present. So this is about the minor. So together with we can define the adjoint of a matrix. So there is one easy way to find the adjoint of a 2 by 2 matrix. That means suppose there is a matrix 2 by 2 matrix A B C D. A is equal to this one. How to find the adjoint of this matrix? Adjoint of a 2 by 2 matrix is nothing but, instead of doing all this work, simply we can write this as interchange the diagonal elements. So D and A and change the sign of non-diagonal elements. So this is minus C and minus B. So this is nothing but adjoint A. Okay. These are all just recalls. So today in my class we introduce some more terms like singular and non-singular, and based on this adjoint we discuss some results. Okay. The first word is singular. So what do you mean by singular matrix? So for a singular matrix, the matrix should be a square matrix. So for any square matrix is said to be a singular matrix. The term is singular. For any square matrix is said to be a singular matrix if determinant of A is equal to 0. That means for any square matrix, if determinant A is equal to 0, then we say that that is a singular matrix. Otherwise, we call that as non-singular matrix. That means if determinant A is not equal to 0, then that matrix is a non-singular matrix. For example, suppose the matrix A is equal to here 1, 2, 4, 8. I take 1, 2, 4, 8. Let's check the determinant of this. So determinant of A is equal to determinant of 1, 2, 4, 8. So this is equal to, you know how to find the determinant of 2 by 2. 1 into 8, that is multiply the diagonal elements minus multiply the non-diagonal elements. 4 into 2 is 8. The value is equal to 0. That means this matrix A is a singular matrix. I'll take one more example. B is equal to the matrix 1, 2, 3. Find the determinant. So determinant B is equal to determinant of 1, 2, 3, 4. So that's equal to multiply the diagonal elements 4 minus multiply the non-diagonal elements 6. So the value is equal to minus 2, not equal to 0. That means the matrix B is a non-singular matrix. So this is about the singular and non-singular matrix. Next we discuss determinant A into I. So this is a first reason. So for any square matrix A, because adjoint A is obtained here. So for any square matrix A into adjoint A, that is equal to adjoint A into A. So equal to determinant A into I. So this is only for square matrix because we have to find the determinant. Determinant is obtained only for the square matrix. Other than the square matrix, we cannot find the determinant. So for that we have to take this result holds good only for the square matrix. So this is the first result. And second theorem says, if A and B are two non-singular matrices, if A and B are two non-singular matrices, that means determinant A is not equal to 0 as well as determinant B is not equal to 0 of same order, then A into B and B into A is also non-singular matrix. These two are also non-singular matrices. That means determinant of AB is not equal to 0 as well as determinant of BA is also not equal to 0. So this is the second result. Next is theorem 3. For any square matrices, for any two square matrices A and B of order n, then we define determinant of AB is equal to determinant of A into determinant of B. So the determinant is a number associated with a matrix. So determinant of AB is equal to determinant of A into determinant of B. So this is one more result. The next result says, for any square matrix of order n, then determinant of adjoint A. For any square matrix of order n, determinant of adjoint A is equal to determinant of A to the power n minus 1, where n is the order of the matrix. For example, suppose A is a square matrix of order 3 by 3. You know the value of the determinant is equal to 4. The question was like that. What is the determinant of adjoint A? So the determinant of adjoint A is equal to determinant A power n minus 1. Therefore, determinant of adjoint A is equal to determinant of A. Determinant of A is 4 power n minus 1, where n is the order of the matrix. Order is 3, so n is equal to 3. 3 minus 1, so this is 4 square. 4 square is equal to 16. So this is the determinant of adjoint A. Or sometimes they will give the matrix itself. So A is equal to 1 matrix. I will assume that this is a 3 by 3 matrix. Find the determinant of adjoint A. In that case, you have to find the determinant of A. Then use this formula. So that gives the determinant of adjoint A. So for any square matrix A, determinant of adjoint A is equal to determinant of A to the power n minus 1. So this is one more result. There is one important result here. So for any square matrix A is said to be invertible. Invertible means inverse exists. So a matrix is a invertible means that is inverse exists. So what is the condition? So the next result says any square matrix A is invertible. This is invertible if and only if condition. If and only if A is a singular non-singular matrix. A is a non-singular matrix. What do you mean by non-singular? If determinant A is not equal to 0, then only the matrix is a non-singular matrix. So, what is the necessary condition? Necessary and sufficient condition for A has to as a inverse, that is that A is a non-singular matrix. So, from this we we can define the formula for the finding the inverse of a matrix. We denote A inverse as the inverse for a given matrix case, especially for square matrix. So A inverse is nothing but adjoint A divided by determinant A. So actually this is the formula. Since divided by the denominator determinant A is there, we know that determinant A is a number here. So if any number divided by 0 is not defined, for that reason we say that A should be a non-singular matrix. Then only we can find the inverse for any matrix, any square matrix. So this is the formula. A inverse is equal to adjoint A divided by determinant A. So let's see some examples based on these results. The first problem says here, for any square matrix of order, and take the order is 3 by 3, A is equal to 1, 3, 3, 1, 4, 3, 1, 3, 4. So this is A. Then verify that A into adjoint A, that's equal to adjoint A into A. So that's equal to determinant of A into I. So here I is the identity matrix of order 3 by 3 because A is a matrix of order 3 by 3 because of it. I is the identity matrix of order 3 by 3. So what is the identity matrix of order 3 by 3? It is 1, 0, 0, 0, 1, 0, 0, 0, 1. So you have to remember it. Sometimes they will give that I is equal to this much, otherwise they mention that I is a 3 by 3 identity matrix. In that they have to consider this one. I as 1, 0, 0, 0, 1, 0 and 0, 0, 1. Let's check it. A into adjoint A. So before that I will first find out the determinant A. So determinant of A is equal to determinant of 1, 3, 3, 1, 4, 3, 1, 3, 4. So you know how to find the determinant of a 3 by 3. So 1 into, I directly write the value, delete the first row and first column, you get a determinant. 4 into 4, 16, minus 3 into 3, 9. Minus 3 into, delete the first row and second column, you get 1 into 4 minus 1 into 3. So 4 minus 3 plus 3 into, delete the first row and third column, you get 1, 4, 1, 3, that is 1 into 3 minus 1 into 4. That is 3 minus 4. So this equal to 16 minus 9. 16 minus 9 is 7 minus 3 into 4 minus 1 is 1 plus 3 into 3 minus 4 is minus 1. So totally 7 minus 3 minus 3, the value is equal to 1. So this is not equal to 0. Okay. Next find the adjoint A. So how to find the adjoint A? Adjoint A is nothing but transpose of the cofactor matrix. What do you mean? How to find the transpose? So one method is finding the transpose finding the cofactor of each and every element of a matrix. And one more easy method to find the transpose of a matrix. So transpose of A is equal to, this is a matrix, isn't it? Transpose of A is this one. Usually if you use the minor concept, first entry is always plus this entry. This is always minus and this is always plus. So if you expand along R1, you get plus, minus, plus. Here itself you can identify this is plus, minus, plus. A11, minus 1 to the power 1 plus 1, it is plus. A12, minus 1 to the power 1 plus 2 is minus. A13, minus 1 to the power 1 plus 3 is 4. Minus 1 to the power any even number is plus. So this becomes plus, minus, plus. This is the first row. Similarly in the second row, this element actually A21 and the last element is a 2, 3. This is minus. Again you get plus, minus, plus. So this is the cofactor. Actual formula this one. Cofactor of an element aij is equal to minus 1 to the power I plus j into mij. So we have already written this part here. Plus, minus, plus, minus, plus, minus, plus, minus, plus. One thing remains here. Mij, minor of an element. So you know, to find the minor of an element, deleting the ith row and jth column, you will get one determinant, that is the minor. So minor of the first element, this is deleting the first row and first column, you will get the determinant. Right there. So determinant of 4, 3, 3, 4. So use some space. The next one, determinant of the minor of an element is 3. That is deleting the first row and second column, you get 1, 3, 1, 4. 1, 3, 1, 4. And the last one, determinant obtained by deleting the first row and third column, you get 1, 4, 1, 3. So determinant of 1, 4, 1, 3. So similarly, find the minor of each and every element. So here, determinant of deleting the second row and first column, you get 3, 3, 3, 4. 3, 3, 3, 4. Deleting the second row and second column, you get 1, 3, 1, 4. Determinant of 1, 3, 1, 4. And deleting the second row and third column, you get 1, 3, 1. So determinant of 1, 3, 1, 3. So the last entry here, deleting the third row and first column, you get 3, 3, 4, 3. 3, 3, 4, 3. Deleting the last row and second column, you get 1, 3, 1, 3. 1, 3, 1, 3. And deleting the third row and third column, you get 1, 3, 1, 4. Determinant of 1, 3, 1. Actually, by this method we can easily find the cofactor matrix, not the transpose matrix, sorry, cofactor. Cofactor of the matrix A. Let's simplify this. So this equal to plus, you know how to simplify the 2 by 2 determinant, multiply the diagonal elements minus non-diagonal elements. So plus 16 minus 3 into 3 is 9, minus 4 minus 3, 4 minus 3 plus again 3 minus 2. So this is 3 minus 4. Next one, minus of, again 3 into 4 is 12 minus 9, minus of 12 minus 9 plus 4 minus 3 minus of 3 minus 3. So leave some space here because these are the elements. Don't add these terms here. These are separate elements. You must get finally a 3 by 3 matrix here. So 3 into 3, 9. So plus 9 minus 4 into 3 is 12 minus 3 minus 3, 3 minus 3 plus 4 minus 4 minus. So this equal to 16 minus 9, you know the value is 7 plus 7. Next 4 minus 3 is 1, there is one minus sign, so this is minus 1. 3 minus 4 minus 1, here plus sign, plus into minus is minus, so again minus 1. 12 minus 9, 3, there is a minus sign, so this is minus 3. 4 minus 3, 1, 1. 3 minus 3, 0. Anyway, this is 0 itself. 9 minus 12 minus 3. Here plus sign, so minus 3 itself. 3 minus 3 is 0, so this is 0. 4 minus 3 is 1. So this is the cofactor matrix. So this is the easy way to find the cofactor matrix. Otherwise, you have to write the formula, then find the cofactor of each and every element of the matrix. Then substitute here, you get a cofactor matrix. Okay. Now we have to find the adjoint of a matrix. So I'll write here. The cofactor matrix is this one. So cofactor of A is equal to 7 minus 1 minus 1 minus 3 1 0 minus 3 0 1. Therefore, adjoint of A is nothing but cofactor of A transpose. Transpose of this cofactor matrix. What is the transpose of this cofactor matrix? 7 minus 3 minus 3 minus 1 1 0 minus 1 0 1. So this is the adjoint of a matrix. Now we have to verify this one. A into adjoint A and adjoint A into A is equal to determinant of A into I. So let's find this one. Adjoint A into A. So adjoint A is this one. 7 minus 3 minus 3 minus 1 minus 1 1 0 and minus 1 0 1. So minus 1 0 1. This is adjoint A and the matrix A is 1 3 3 1 4 3 1 3. You know the matrix multiplication. Multiply these two. 7 into 1 7 plus minus 3 into 1, that is minus 3. Then minus 3 into 1 minus 1. So this is the first entry. First row, first column. First row, second column. First row, third column. These are the entries of the first row. Second row, first column. Second row, second column. Second row, third column. These are the entries of the second row. And third row, first column. Third row, second column. Third row, third column. These are the entries of the third row. So 7 into 3, 21 plus minus 3 into 4 is minus 12 plus minus 3 into 3 is 9. Then 7 into 3 is 21 minus 3 into 3 is 9 minus 9 minus 3 into 4 is minus 12. Next, minus 1 into 1 is minus 1, 1 into 1 is 1, 0 into 1 is 0. Minus 1 into 3 is minus 3, plus 1 into 4 is plus 4 and 0 into 3 is 0. Minus 1 into 3 is minus 3, plus 1 into 3 is 3, plus 0 into 4 is 0. Next, last row. Minus 1 into 1 is minus 1, 0 into 1 is 0 and 1 into 1 is 1. Minus 1 into 3 is minus 3 plus 0 into 4 is 0 plus 1 into 3 is 3. Minus 1 into 3 is minus 3, 0 into 3 is 0 plus 1 into 4 is 4. So this equal to, the matrix is 7 minus 3 plus 1, 21 minus 12 minus 9, minus 12 minus 9. What is the value? Minus 12 minus 9. Minus 12 minus 9 is again 21 plus 21 minus 21. Here 0. Here 21 minus 9 minus 12. Again this is 0. Then minus 1 plus 1. Minus 1 plus 1 is 0 here. Minus 3 plus 4, 1. Minus 3 plus 3, 0. Minus 1 plus 1, 0. Minus 3 plus 3, 0. Minus 3 plus 4 is 1. So this is a adjoint A into A. So similarly, you have to multiply A into adjoint A. So first write the matrix A, then write the adjoint A. If you take the multiplication of those two matrices, finally you get 1 0 0, 0 1 0 and 0 0 1. I call this as equation 1 here. Now I will find out here the last part, determinant A into I. So determinant of A into I. So determinant of A we know it is 1. So 1 into the matrix 1 0 0, 0 1 0 and 0 0 1. You know this is the scalar multiplication of a matrix. Scalar multiplication of a matrix is nothing but multiply each and every element of the matrix by a scalar. So that means multiply each every element of the matrix by 1. You will get 1 0 0. 0 1 0 0 0 1. So comparing equation 1 and equation 2, we can say that we verified the given result, that is A into adjoint A, that's equal to adjoint A into A equal to determinant of A into I. So this is the verification. So one thing is you have to take care of the cofactor matrix. If that is clear, then you will get all the terms clear. So this is one example.